Okay, so as you can see, I'm wearing the same thing as last time because I'm trying to knock out a whole bunch of these at once while I am on Christmas vacation. So you're going to hopefully have most of the course material you need to crush CS-330 right at the beginning. And you can take these, take your time doing it. But again, I'm not giving you the solution in these videos. I'm just giving you the information on how everything works, how to do things in a good, clean way, and then you can use that knowledge to complete your assignments and hopefully have a nice bit of code at the end. So last time, what we did is we set up the window and we got it showing a nice red color. We're going to continue on that. We are going to draw our first triangle today. We are going to set up a shader, and we are going to have the shader draw a triangle with colors that do a gradient. Now, we're going to do it in a non-abstracted way at the beginning, which is going to show you, it's going to give you all the information on how everything is working. And then just like we did with the application class, we are going to abstract it all out so that we can reuse these different components throughout our application so that we can do a whole bunch of cool stuff all at once, right? So without further ado, let's just jump into it. These lessons, I realize, are probably going to just be long lessons because there's no reason not to be a long lesson. But basically, this is week 2. This will give you all the knowledge you need to complete your week 2 assignment. And then I'll try to separate them out in weeks. So you can have a nice 1-2 hour video tutorial that'll teach you how to do stuff nicely, teach you how everything works with explanations on everything too, don't forget, and we will move forward. So now, let's just jump onto the screen and get started. So like I said, I'm going to do everything in my CMake project, which we set up last week, but everything that I do will work in in Visual Studio. But just remember the process that you will need to go into the Visual Studio with any files that we end up adding, which we will towards the end of the lesson. Any file you end up adding here, you need to go in and manually add to your Visual Studio project afterwards, because otherwise it's not going to work. I'm going to try to remember to show that process at the end of the video. Just go in and add the various files we haven't added yet. But if I don't, just remember that might be why your Visual Studio project isn't working. Or whenever you see me create a file here, remember I usually create it in the, so I would go inside here, I would go into my source folder and create a file. I would go inside my include folder and create a file. And then I would go in and manually add those to my Visual Studio project, right? So, that being said, let's get started. So we are going to start our hello triangle. The first thing you need to know about triangles, and this is going to be I'm going to use the data here, or the pictures here to kind of describe what I'm talking about. So all triangles are built by a series of vertexes, and a vertex is a point on a triangle. So if you see a triangle here, so this is a triangle. A vertex is one of these points that make up a corner on the triangle. And when you have an object which is built out of many different triangles, you have a whole bunch of these points, and then you tell it which 3 triangles are a face of the triangle. So when you have a vertex, which is the individual points, and the face is a combination of 3 vertices, which is the plural of vertex, which will tell you what the face is. Something that might not be mentioned here, but I'll mention here now, which is important to know, especially when we get to lighting. The triangle face has a front direction, right? So what that means is that, let's say, maybe I'll open Paint so I can maybe do this in. So if you have a triangle like this, so you have a front direction. So let's say you're pointing out like this. And you have a back direction, which is, oops, reals. I don't like the new paint. But anyways, you have a back direction that points out like this, right? And it's actually important that you tell the renderer and your shaders which way is forward and which way is backwards, right? So by convention, there is a specific way that you tell your shader this, and this is by the order in which you give the vertices to your renderer. So if you want the front face, you can either give it to it in a clockwise order, like this, or a counterclockwise order, which is, as you could guess, like this. Now, I believe the convention, what is usually used, is counterclockwise, and that's what I'm going to use here. That means that when I give my 3 vertices to my renderer, I want to start with this one, then go this one, and then this one. Or I start in this corner, go to this corner, and then this corner, or I can start in this corner and go. As long as they're counterclockwise, everything will work correctly. Or clockwise, depending on what you set up, right? So that's the idea. It's important. We're not going to use that right now, other than when we define our vertices. I'm going to try to remember to always do that in the specific order. But later on, when you're building your objects, if you don't pay attention to this, when you get to lighting, everything's going to look bad, and you're not going to know why. So just remember, when you're defining your faces, always provide the vertices in a specific clockwise or counterclockwise order, and I will show you how to define where you tell your application what you're doing, right? All right, and we're also going to make it so that you can't see the back of your faces. That is, 1, a performance optimization, but 2, it will also make it obvious when you screwed something up, right? And I'll point that out as well. So your vertices are a series of points, and these points contain data. The data on these points will generally, and we're going to start with just this, we'll just have a position, which is going to be the X, Y, and Z coordinate of where those vertices are in 3D space, right? And this is going to be in what's considered local space, but we'll get into that a little bit later. Transformations makes it quite clear. But basically, you have vertices that are positioned in 3D space using a series of floats. So that data, what it would look like is, this is what it would look like to have 3 vertices and their 3D space defined. So this, you're going to see the Z value is 0 for all of these, meaning that they're right on the plane. They're all on the same plane depth-wise, because Z goes into your screen. But you have one in minus 0.5, minus 0.5. That's to the left, and I believe it's going to be down. Then 0.5, which is to the right and down. So these are the bottom sides. So you see here, it's your bottom side of your triangle. And then 0, 0.5 up. So that's going to be right in the middle. And 0.5 up, which is going to be here. So what you're defining is, again, bottom left, bottom right, middle. And you see that it's been supplied in a counterclockwise order. That was done on purpose, but I don't know if it's mentioned on this page. If it's not, I did it for you. Now, along with this position data, you can also supply other data, like vertex color, which we will see later on in this episode lesson. UVs, which are important for which that defines. So here, UVs will UVs are to tell you where, if you have a texture on your face, which portion of the texture is assigned to which variable on the face. We'll see that when we get to textures. There's normals, what it says is which way is the front facing out. What direction is perpendicular to your face is technically the definition of a normal, and that is used for lighting. So if your faces are determined in any which way, and you try to supply normals to those faces, because usually you'll calculate your normals based on the faces, your normal directions could be all wrong, which means that the light will bounce in the wrong direction, which will make everything look like crap. And those are the main things. There might be some other stuff, but we'll see stuff as we go through. So the first thing we need to do is define our vertex data. Now, you can see here that you can define, in the end, the vertex data that we're going to pass throughout this entire course is just going to be mostly 99%, all just a bunch of floats, floating point values. Now, you can define them as just an array, a naked array of floats, but that is not the greatest way to do it, right? So what we're going to do now is we're going to actually add another library, which will make things a lot easier. We're going to use a library called GLM. So we're going to just look at GLM here. Now, you saw that in our first lesson when we set up the sample project that we added GLM. Now, GLM is a mathematics library for OpenGL. OpenGL Math, right? And all it is it's a header library, if I'm not mistaken. It's just a header library that has a bunch of math types on it. So we're going to do things in a more structured way right from the beginning with our vertices, because it's really hard to unwind bad vertex setup. Well, it's not hard, but it's annoying and you don't want to do it. So we're going to use this math library because we're going to use it later in one of our, we're going to need it. I mean, it's part of the course material. So we're going to put this in now and use it. So GLM, since it's just a header library, we don't need to build anything. It can go inside our shared libs here. So we're going to actually add that as a submodule as well. So you saw that I went to github/gchook/glm, and I just got the URL again. And again, we're just going to say git submodule add link. So it's going to CS-330 showcase app /external/shared/glm. All right, I misspelled that, so let's do that again. Git add URL, and this time I'm just going to say git add URL and CS-330 showcase app. All right, that should put it in the right spot. Yeah, it put it in the right spot. Delete this. All right, so now we have GLM in our project here, in our Git submodules. That's good, and we have it here. Now what we want to do is go into our CMake list file and do basically the same thing we did with GLFW. We are going to add subdirectory external/shared/glm. And again, in here we just put GLM, and at the bottom here we put GLM. All done. Now we have GLM in our project. To do the same thing, I showed you how to add GLM in the first lesson of this series. So if you're wondering how to do that for your Visual Studio project, you can literally add the submodule the same way if you wanted to, and just add GLM the same way we did with that initial thing. You'd put it in shared or in VS Libs if you're only doing Visual Studio, and you would just add this GLM folder, this top-level GLM folder, as your inside the VC++ directories option in your project properties. Inside your include directories, it would be project dir slash external/shared/glm in this case. We'll probably do that in a bit. All right, so we have GLM. We've added it. Now we should be able to simply, if you see here, include GLM/glm.hpp. We have it, right? So we're going to add a set of types, talking about these vertex types. So we can define an array of floats. So each vertex, let's go back to learn OpenGL here. So each vertex is 3 of these floats, right? When you send data to the GPU, which we're going to be sending these vertices directly to the GPU, you send basically the raw binary data. So in C and C++, when you create, I'll do it in here. I'm going to make a header file because we're going to need this anyway. When you call this types, we're going to add this. I'm going to say pragma once. I'm going to add. I'm just going to include vertex types.h like this. So let's go back to types. That's just to clean stuff up. And I think it didn't do it. Good. All right. So what it was doing, let's just copy that piece of code in. It was doing this, right? Float versus equal to this, right? Now, anyway, so this is 3 floats, right? So this in memory is the same as if we had a struct that had 3 floats. So this might make more sense. This might be a good way of explaining. So we have a struct of 3 floats, and float 1, float 2, float 3. So a struct, if you don't know, a struct in C++ is just a class that everything is automatically public, right? So this is pretty much exactly the same as this. And in memory, it's the same thing. But usually when you're working with raw data like this, you wanted to use a struct. All right, so this in memory is the same as 3 floats right next to each other inside an array. So it's the same thing as if we did this, right? So extrapolating from that, if we make a struct of float 3s like this, then we can have, let's just put all that data back, float 3 like this. Then we can initialize our vertices like this, right? And this is the same thing. So now we can technically, if you wanted to, you could call this vertex. Call that vertex. And you can say this is position X, position Y, position Z. So now you can define them, and it makes it so that you know what each one of these are. But in memory, this is exactly the same as what we had before. Now, to make it even simpler, because we're going to need more stuff, and we don't want to separate everything like this, we use a GLM library. We're going to include GLM sets GLM HPP. Now, a struct of 3 floats, like we had when it was defined as float 3, we can do as GLM vec 3, and we can call this position. Now, if you do this, it's going to make things look a little bit more complicated inside here when we initialize everything like this, right? Now, let me finish making this like this. And one more. And one more. All right, so now this looks a little bit intimidating, right? So you don't really know what's going on. So what you can tell right now, and this is the thing, is that this is a array of vertices of vertex struct, which each one, so that this one, when you do this, this initializes it in place. So it's just like if you did vertex like this. So you're creating a vertex, and each one of these is a GLM vec 3. And in memory, remember, all of this is in memory. It's exactly the same in binary as what we had before with just the naked arrays. Now, the advantage to this is that now you can you'll know exactly what you're doing, because if you want, and with C++20, there's a nice feature, you can do this. Oops, dash capital position. And this is why one of the features that I will be using in C++20 that may not like that. So now you know, oh, these are the positions. So when we start adding more data to this vertex, right? And we will be, you're not working with this ugly, let me copy that again. You're not working with this ugly array, which you have to be like, okay, so like this, it's a little bit simple. You have each vertex on one line, right? So now let's say you want to add UV data, right? Or actually, let's make it color data, because we're going to be doing color, right? Well, we're going to add color. So what do you need to do now, right? So you know that this needs to be, this is how you need to pass it into the GPU, is as a vertex data that represents a vertex tightly packed together. So you need to add the color data at the end of these vertices, right? So let's just say you want it all white. You want every vertex to be white, right? You need to add this to every line. Every single line, every single vertex, you need to add this, right? I'm having trouble. All right, so now you have all your vertices. Simple enough, right? But what happens when you add UVs? And what if you need to change this data? you need to remember exactly which part of this giant array of numbers corresponds to which data. And you can do stuff like you can make a position, and then you can add some tabs, and you can put color, and that like technically doable and a little bit better, but it makes it annoying, right? But what if you just want to do this? You can just say dot color equal 1.f 1.f .f and 1.f, right? Take that off. Now, what is wrong with my code? Vertices, redefinition of vertices. Oh, redefinition. So here, raw array. We'll just do this. All right. So now you can see that when you need to change something, like, oh, I want to change the color of this vertex. Well, there's a position called color. Now, if you're using something less than C++20, which you might have to, the instructor might not be happy. You could do this the same way in older versions, just without these labels, right? And then if you want to, you can put a position color here to remind yourself. But in general, it's just in the same order as this one here, so you don't even need to write this every time. But anyways, I do it like this because it makes it very clear on what you're working on. But can you see how working with a vertex like this is much more preferable to working with a raw array of float like this? And again, as you add stuff, you want to add UVs. So if you initialize UVs like this, right? So if you just add UVs like this, like to UV, right? So here, I'm initializing my UV with a value of 1. I don't need to go and add UVs to every single vertex if I don't need that data yet, right? So by doing this, so I can like, let's say I want default color of my vertices to be white, and I want a default position of my vertices to be 0, right? Now I technically don't even need any of this. I could just say I want 3 vertices in the exact same spot, exact same color with same UVs, and I don't need to do any of this. And if I don't want to add UVs, I don't need to go through this giant array and add them for every single vertex, right? So this is what you need to think about when you're programming, is you want to make a structured class that will automate some stuff for you. So in this course, we're going to use this vertex. And frankly, the only thing we're missing here is normals, so we'll add normals here now, just so we don't need to do anything later. So we got normals. So that defines our vertex class, and we don't actually need this. Another thing is we won't be working with raw arrays. We'll generally be using either standard array or standard vector, usually standard vector, just for, again, ease of use stuff. So we'll take this, and I'm actually going to copy this because we have the values we want there. So let's go into and actually implement this. So what we need to do, the structure of our triangles are going to be built out of these vertices and our vertex struct. So one thing that we're going to do is in here, this is a loop, and this is usually called your game loop. Now, usually what your game loop is going to be set with update, and it's going to have a draw command, right? And usually you're going to want to do those in separate functions. So let's just define those now. So we're going to call one update, and we're going to call one draw. And I'll just put them in order. Generate, and again, it's the same in writer. It's the same. All right, update and draw. And now we will call update and draw. This will just allow us to do stuff in a specific way. All right, so now the draw command, so first let's put these vertices here, just so we don't forget them. Our draw command will be in here, GL clear color. So all of this is our draw loop. All GL stuff is generally in draw. Boom. I don't know why I made those bools, but whatever. That's going to return false, and we might fix them later. our update is going to change stuff during the scene, but what we're going to also do is we are going to have a setup scene, set up the scene function at the top as well. So we will call void setup scene. I don't know why I made that rule. I think I was just copying open window and like while I was talking, but let's generate that. Come on, generate it. All right, so we're going to take this. We're going to move this above update where it belongs. Update does nothing right now, but our scene is going to be like this. All right. So these are our vertices. We're going to make this a vector. So to change it from a vertex of a raw array of vertices to a vector, we literally just need to do std vector vertex, move this, and then include vector. And that should fix that. Now we have a set of vertices, 3 vertices, exactly where we want them. Same place we had in the Learn OpenGL, right? So to begin, we will want to, so these vertices need to be uploaded to the GPU so that when the GPU goes to draw them, it knows that it has the data. So you do this by providing it a array buffer or a vertex buffer, right? So to create a vertex buffer, so I'll show you how to create it and I'll give some explanation. So to create a vertex buffer, you're going to need a vertex buffer object, right? And a vertex buffer is literally just an array of data. It's just binary data in the shape of an array. And it could be an array of arrays, but we don't want to get too complicated. It's just an array of data, generally an array of vertices in this case. So to create your array, you will do unsigned int unsigned int VBO. So that's a vertex buffer object. I'm actually going to be explicit, just so you know what all this is. Vertex buffer object, it's not initialized to anything because we initialize it using GL gen buffers. We'll say we want 1 buffer, and we want to store that buffer into vertex buffer object. Now you can see that if we want to make this an array, let's say we want to generate 3 buffers, we can just put 3 like this. But we don't need to do that. We only need 1 because we're creating a single triangle. Create the triangle. That creates a buffer. Now the next thing we want to do is we want to bind the buffer. So binding the buffer tells OpenGL, oh, okay, now every time I do an action on whenever I want to manipulate here, let me just write it down so I can tell you be GL array buffer VBO. So basically vertex buffer object. So what this is basically saying is whenever I make manipulations on the GL on a GL array buffer after this call, it's going to affect the vertex buffer object. So it's the very common pattern in OpenGL. You're going to bind a resource and you're going to use that resource or act upon that resource after the bind call. So if you're using multiple objects, you're going to have multiple vertex buffer objects. When you're working with each one, you need to bind them as you need them. And then we want to upload the data to the GPU into our vertex buffer object using GL buffer data. GL buffer data. So we want to act on the same buffer type, array buffer, as we just said we were going to work on. So the size is going to be, so it's going to be a little bit different, but it's going to be, since we're using vectors and vertex structs, it's going to be a little bit simpler. You're going to take the vertices dot size. So this is the integer size of the number of vertices you have. So in this case, 3. And you're going to take times the size of each individual vertex, which is going to be however much this is. Now, again, one of the benefits of using a vertex struct versus blind arrays is that if we add data, remove data, that size of call is going to automatically resize itself, and you're not going to have to worry about it. So you can add stuff, remove stuff, and it'll just keep on working, right? And that's what you want. You want to make stuff as easy as possible for yourself as you go through this. So you tell it how much data are you putting in the buffer, which is in bytes. That's why you do size of vertex gives you the number of bytes per vertex times size, which is 3. So 3 times the size in bytes of each vertex. Then you give it the vertex data as an array. So it's a pointer to the front of the array. With vector, you can access this by doing vertices.data. Now you can see when I open this, come on. You can see it returns a pointer to the inline type. So it's a pointer to the first data member of that array. And vectors store stuff as contiguous memory, which means they store them basically as arrays under the hood. And again, you're going to use it for a GL static draw call. Okay, so there's actually an explanation on Learn OpenGL. GL static draw basically says that the data is only going to be set once and used a lot. GL stream draw says it is set only once and used a few times. And dynamic draw means the data changes a lot and is used many times. So that's the difference. So generally, most of the time, you're just going to be using GL static draw because you're not doing anything fancy in this course. All right, so now that we have that, so this sets up the vertex buffer. Now, we need a few things to do this, but for now, what we're going to say, we need access to the vertex buffer object when we go to draw our triangle later. So what we're going to do for now is we're going to store it inside our class here. So we're going to say, I think you can do TLUint, I'm pretty sure. VBO, vertex buffer. And then what we're going to actually do is in here, instead of declaring it there, we are just going to put it inside our GLGen buffers here. And again, it's not initialized, so let's just initialize that, right? All right, so now we create our buffer object and we have access to it. So when you are drawing something in newer OpenGL or any modern application, you can't just draw directly to the screen. You give it the buffer for all the vertices, which is what we just did. And we also have to give it some shaders, which will which tell it how to draw stuff on the screen. Now it gets a little bit complicated in how we do this, but in general, what we want to do is we are going to create a vertex shader which transforms where the vertices are in space and where they're going to be drawn relatively on the screen. It transforms them from what's called local space into, I believe, what it's called clip space, I think is what it ends up being called. But basically, you're giving it a triangle in a specific shape, and by the end of your vertex shader, it's going to say, no, it needs to be drawn over here because the camera's over here, you're looking through a tunnel, that kind of stuff, right? After the vertex shader, simplifying everything down, you're going to go to the fragment shader. There's some other steps in the middle, but you can ignore them in our case and throughout this entire course. Goes from the vertex shader to your fragment shader, which says which color is this pixel. It's not technically a pixel, it's a fragment, which is why it's called a fragment shader. But most of the time, it's almost always 1-to-1 pixel to fragment. So you can think of a fragment as a pixel. So when you get to your fragment shader, it asks, basically you're telling it what color the pixel is going to be at the end, right? So I highly suggest you read through Learn OpenGL to get a more in-depth explanation of how all of this works. What I'm talking about, but as a basic idea, that's what it is. A vertex shader, where is the vertex in space? Fragment shader, what color am I? So what we need to do now is we need to create some shaders. Now the very simplest shaders, and I'll show you this now, and what we're going to do, and I'm going to do this in week 2 might end up being 2 videos, but the vertex shader is going to look something like this, but we are actually going to have more because we made a larger vertex then. than this. And then we have a fragment shader, which is going to basically just give it a color. So we're going to create our shader programs. Now, the way that they do it in our samples and the way that they're generally expected to do it in here is they make string literals and then they just compile those string literals. So what we're going to do is we're actually going to do the same thing in here, right? We're going to make our string literals, but we're going to move them to files afterwards. So to start, we're going to create our fragment shader, so our vertex shader. So we're going to do this in the setup scene as well, because I'm going to move them. So create vertex shader. All right. So we're going to say std string vertex shader equal to, I think I can do this. All right. So these are raw string literals. They were introduced in, I think, C++ 17. You can do them. I'm going to show you how they do them in Learn OpenGL. You can do them like this, where you just put new lines at the end of everything. But I don't want to do that. So raw string literal. So this is going to be version 334. So remember, we set our OpenGL version to 3.3, which is where this 330 comes from. Now we're going to have a few things. So layout, we're going to have layout. I think I can do that. Location equals 0 in vec3. We're going to call this position. I don't like using abbreviation. So I'm going to actually move this type here so we can see we're getting. So we can see that position is in the first position, or 0, and it has 3 floats, vec3. See, vec3, vec3. We are going to say the next one, layout, location equal 1, in vec3 color. And you can see how this goes. Layout, location equal 2, in vec3 normal, and layout, location equal 3, in vec2 UV, right? And this one's actually going to be very simple. We want a void main function. We open curly brace, close curly brace, and we say GL underscore capital P position equal a vector of position.x, position.y, and we can actually just do this, I'm pretty sure. All right, and that's going to be our vertex shader. Now, what this is basically doing is saying this is the format of our vertex, which matches what we're passing in, and we want the position of the vertex to literally just be the position of the vertex as passed in, no transformations. And I'm not entirely sure what the one at the end does. I believe it has something to do with the way that you transform when you're doing projections for the camera. That will become like 0.5, which is what it's going to divide everything by. It's some math stuff. You can look it up on exactly what that means. But in the end, this will be something else entirely by the end of this course. All right. Now our vertex shader, we're going to just skip some stuff. We're going to define our vertex shader at the same time. String fragment shader, shader equal R, like this, string literal, like this, and we will say same thing, version 330 core. Now you always want to put the version at the top and make sure there's no spaces here because it needs that as the first line in the file, if I recall correctly. All right, so we say here it's going to be very simple. It's going to say out vec4 frag color. So one thing I should mention, in keyword means it's coming in as an input, out is an output. So your fragment shader always outputs a frag color, and your vertex always has as input the vertex stuff here. So out vec3 frag color. And then again, we just have a void main function. And this one's going to be very simple. We are going to say, again, we could pass this color through, but we will do that towards the end of the lesson when we just make everything work a little bit further. So void main like this, and we say 1.0 frag color equal vec4, and we're going to make it the same color as learn OpenGL for now, like this, 0.2f and 1.0f. Weird. I could swear that Vulkan doesn't let you put these f's here, but it seems to be accepted here. So we have our vertex shader and fragment shader. So to create our vertex shader, we are going to just do this. Unsigned int vertex shader GL. So vertex shader, I don't know why this is two lines, equal GL create shader GL vertex shader. There. And we actually can just do this. Auto. And this will be source, vertex shader source, fragment shader source. And then our fragment shader, well, we'll finish building it. So then we want to compile the shader, GL shader source. We want to do it in our vertex shader. We are compiling a single shader. We want to compile our shader source, vertex shader source, and we can just pass in null pointer. I don't know what this one does, just pass in null pointer. Dot what if I do this? Can I just do this? We're gonna make these constants just because that's what we're gonna do. This is gonna make them constant characters, which will go nicely with this. Usually I would put these in strings, but I can figure that out later. All right, so I think I could just pass in .cstring. Whatever. We'll just leave that for now. Then we're gonna go GL compile shader vertex shader. So then we want to check if compilation is successful with this, which we will do by doing int success character info log. Now I'm just copying this from learn OpenGL. You can make this fancier if you want, but get shader IV vertex shader GL compile status and success. Then we will do if it's not successful, we say GL get shader info log vertex shader maximum amount null pointer info log, and then we can print it. So std error shader vertex compilation failed info log line. All right. So failed to compile the shader. Now doing the fragment shader, you can imagine is very similar. So we're just going to copy paste this. And we'll say fragment shader and replace this all with fragment shader source. We don't need these because they're already there. Fragment shader, and then we can just change this to fragment. There we go. So we have our fragment shader compiling. It's exactly the same. And then what we need to do is we need to create a shader program. Skipping a step, we're going to need reference to the shader program later. So again, we'll say GL uint shader program this, and in here we will create a shader program. So we're going to say shader program equal GL create program like this. Then we are going to attach these two shaders we just compiled to our shader program. And this needs to be GL fragment shader. Sorry. Vertex shader, GL attach shader, fragment shader. I'm trying to go quick because I'm running out of time. I gotta go real soon. So the shader program like this, shader program like this, and then GL link program, GL link program, shader program. There we go. And then we can delete the program, delete the shaders that we created because we don't need them anymore after we create the program. Delete shader, vertex shader, GL delete shader, fragment shader. So after we delete these shaders, what we're going to actually do is we're going to go back up to where we linked the program here. We're actually just going to put one more check on it. All right, one more check here. GL get program ID, which again is to get. It's used to get the success status of the thing. So we say gonna be shader program GL link status, and inside our success variable, if not success, then we will basically do the same thing as here. So we're just reusing this like this, and we will say should shader. I can say geez, what's going on here? I'm gonna hide this for now just because that's better. All right, so we did a compilation fail. We'll put link fail. So this is just going to be so it tells us whether or not it worked. So we're gonna press play here. What did I screw up? Return truncation. Oops. False. Condition is always true. Oh, and then true. Weird that didn't give me that. I guess it's a warning error. Use designated required at least C++20. Oh. So I set it to 20 here. In my CMake file, I need to set it to C++20 CMake. So we did a lot all at once, so I'm just kind of making it up, fixing any issues that come up. So the next one here, in here we can just set it to C++20 like this. This one, sorry, it's actually this set CMake CXX standard 20. So I can either set it directly on the project here. That was the set target, whatever. But I'm just going to set the entire CMake thing into it. Use the same standard, and it builds. And now will it link? We'll just look at the log. So you see that we don't have any logs in here. So that is safe to assume that we didn't get any of our compilation failures. So with that done, we can assume that all these shaders are working correctly. And now we have a few things left to do. So now we have our shader program. When we want to use the shader, before we call draw, so it's going to be like a draw, some GL draw called here. Before we call draw, we'll need to activate the shader. to say everything that we're about to draw is going to use these shaders or this shader. So we use GL, use program, shader program, like this. And we're just going to say use our triangle. Right? So now if we go to try to draw the triangle now, it's not going to work. So even though when we bind a shader and when we send vertex data for the draw call, we need to tell the shader the shape of the vertex. So the shader, it's defined like this, right? 0, 1, 2, 3, like this. Now we have to tell OpenGL that the vertex buffer that we're sending in has this format inside. And we tell it that because it does some automatic separating of your buffer data based on the size of everything. And yeah, and it doesn't assume that you're passing incorrect data. It takes what you tell it and then processes it. So I'll show you what we need to do, and then I'll break it afterwards so that you can understand kind of what I'm talking about. It's difficult to explain, but basically we're about to tell it the buffer data that we're giving you is in this shape here. Or technically it's in the shape of our vertex class. I'm going to open this again. Let's split and move right. Close this one. All right, so basically all we need to do is we need to before we call our use program, when we go to draw, there are several steps. The first one is you're going to bind your buffer. So you bind buffers for the object you want to draw. So in this case, it's our vertex buffer array. So we'll call GL bind buffer vertex buffer object. And this is, we also have to tell it what kind of array it is, what kind of buffer it is, the GL array buffer, vertex buffer object. Now we called bind buffer up here, if I recall correctly. We called bind buffer here. Technically, this is just technically, your buffer will stay bound until you either unbind it explicitly or bind something else to the same slot. So we technically, in this case, don't need to call bind buffer here, but in a real use scenario, you're usually going to be calling bind buffer before you for each object. So we're just going to do this so we can, when we abstract things out, it's easier to do one step at a time. Then the buffer data is already in the buffer, so we don't need to upload it. The next step will be to define, give the GPU or OpenGL or your shader object the shape of your vertex. And you do that one attribute at a time. So each one of these is considered one attribute. And I wish the shaders are not in a separate file yet, but it will. You'll see what I'm talking about. So to do that, we're going to say define. We'll say define vertex attribute. So you do that by doing GL vertex attrib pointer. This takes a bunch of different fields, as you can see. The first one is the index. So if you look up here when we created our shader, here it says location 0, location 1, location 2, location 3. That's the index in this in this array. So we're going to do position first, so 0. Second one is size. So how many elements does this attribute have of the given type? So I'll show you what that means. So in our case, position, as we discussed earlier, has 3 floats. So it has 3, and the next one, GL float. So it has 3 floats. this one is whether or not it's normalized, so whether or not all the values are going to be between 0 and 1, or whether, and it might, I think if you say true, it might convert it to normalized values if you, or something, but in this case, we're just going to say GL false. So size here, this is going to be in bytes. This is the stride. All right, so this is what's called a stride, and this is called the offset. That makes sense. Okay. So I just put that there so you can see. So these ones here, the stride is how many total bytes are in a vertex, right? So basically, we're going to give it a, let's say we have a, let's just assume, I'm not going to do math, but let's just assume a vertex is 4 bytes, and we have 3 vertices. So our total array is going to be 12 bytes, right? Now the stride is how many of these bytes is a single vertex, so that when it splits it up with the GPU, it splits it up with 4, 4, 4, right? So the stride in this case, in this made up case, is 4 bytes, right? So the stride is the size of your vertex. So you can literally just do size of vertex. Now, offset is the position or the offset from the beginning of the structure of this stride from the beginning of it to the attribute that you're defining. So in this case, we're defining position, and there's a handy function that works with structs and classes. You can do offset of vertex position. I think that didn't work. How do I? Oh, I think I need to do what? So this needs to be a void pointer for whatever reason, just the way the API is made. So you just cast the void there. Now I don't generally like doing C style cast, just because otherwise reinterpret cast. Okay, reinterpret cast. I think that's going to be right. Well, we'll come back to this if it's not working, but this is the general idea. Now we need to do this for every single one of these. So it's really going to be fairly simple. We're going to paste it 4 times. You're going to have color, which is three floats as well. So vec3 is 3 floats. Size of vertex, but the offset is color instead. Normal, same, 3 floats, but its offset is normal. And UV is a vec2, so 2 floats, and the offset of UV. And those are your attribute pointers for your vertex. So this tells the GPU that, hey, your vertex is going to be this big. Oh, sorry. We also need to update the indices of all of these to match the order that we expect them in our shader. So this is going to tell the OpenGL is going to know that when it's passing vertex data, or the GPU knows that when it's parsing vertex data from the array, it will use this stride, the size of vertex, and the members at the various indices are going to be according to these positions in the struct, right? Hope that makes sense. And then we need to enable these vertex attribute arrays as well. So we also will do GL enable vertex array attrib. Vertex attrib array 0. I think we need to do this 3 times. Or 4 times. Yeah, then we do this 4 times. Right? So we enable all of these. And then with that done, we use our program and we can finally make our draw call. So here we can actually just put GL draw arrays This should be GL triangles 0, 3. Right, so what the GL draw arrays does is that the mode is in triangle mode, so you have different modes of drawing. There's GL triangles, there's GL elements, I think. Maybe index. It's probably GL index, which we'll look at a little bit later. And then there's GL triangle strip, which does things a little bit differently. But for now, you can just assume that for now we're using triangles. We'll go to element arrays, and that's probably as far as we're going to go because that's all we really need. The second one is the first index inside your vertex array that we bound that you want to start it at, and how many elements you want to draw starting from that thing. So we've got a buffer that contains 3 vertices. We just want to draw 3 vertices. So let's see if this worked. It'd be interesting if it does. It didn't work. So why didn't it work? Good question. Why didn't this work? Am I calling setup scene? I'm not calling setup scene, so that'll probably help if I call setup scene. Okay. So now I'll actually know whether or not any of these mistakes or anything is broken. All right, so it actually doesn't compile. So cannot convert from const for float fragment compilation failed. Oh. Well, that makes sense. Which part did I screw up? Oh yeah, you guys might have been yelling at me this whole time. This should be a Vec 4 frag color, not Vec 3, because there's an alpha value here. All right, let's try that again. Okay, there's no errors. So the shader is doing its thing. Huzzah, we have our white triangle. Okay, so I think the mistake we were making here is we were calling GLU's program and we were doing these and binding the buffer. GL bind buffer, where is it? Sorry. GL bind buffer. GL bind buffer, GL bind vertex array. GL bind buffer like this. So when you, I think this is the mistake we were making. I'll cut this and move it to the front before I made the vertex array change. Yeah. So I just had this in the wrong order. You want to bind your shader before you bind all your vertex attrib array stuff. But before that, bind vertex array. So we're going to move a little bit forward. Maybe it's just because I'm not using vertex array objects, which doesn't make sense to me. But we can see. So if we go back to our setup scene, when we create a lot of this stuff, actually, we can actually move these here into our setup scene once we define our shader at the end here. So let's use the vertex array. So all of this stuff is defined on a per object basis, or it's very common to have to switch all of these fairly often. So some of your vertices in the real application might not have color data or might not have UV data. We're just packing it all together. So the way you actually want to do it is you want to enable a vertex array object, which is a VAO, which will store the VBOs and the these attrib pointers as well. So we're going to move this a little bit higher up, closer to where we define the buffers up here. Now we're going to put them right underneath the buffers. Now, right before this, we're going to define our VAO inside here. So again, we're going to make a GL uint vertex array object. And here we're going to say GL gen vertex arrays 1 and BAO. Oh, sorry. Vertex array object. Then we want to bind the vertex array object. So we can do here GL bind vertex array object like this. And then we can keep all of these, and then down here when we're doing everything we want to do, we just call use program and then bind vertex array and then draw arrays like this. Bool should be preceded by, oh, I have an extra character in here. So that's how we get our shader object like this. So what's happening here, right? So let's do this one step at a time. So first we create our, this is just going to be a recap. First we create our vertices like this, which is defined as this point, then this point, and then this point. They all have a white color here, which we actually don't take into account. We've got that hard coded. We'll deal with that in a minute. Then since we have, then we tell the shader, or we create a vertex array which stores all of these settings underneath it, so that we, instead of having to bind all of these individually every time we call, we can just bind our vertex array. That's the purpose of a vertex array. So we define, we create our buffer, we upload our vertices to the buffer, we tell the buffer the shape of our vertex using this, which has to match both our struct and what's in our shader. So everything needs to match. We then create a vertex shader, which takes in as values, as input, the different attributes of the vertex, and then outputs the position of the vertices to the screen. Then we define our fragment shader, which right now is just going to give us a solid white triangle, so every pixel will be white. Then we compile these shaders that we just defined. We linked them together just like you would a C++ program. You compile things and then they link together at the end. And then we store everything and delete the temporary objects. Now every frame we clear the screen of a specific color. We say that we're going to use the specific shader that we set up. We bind the vertex array that we set up, which basically says this is the shape of my buffer, or my vertex, and this is the buffer that's bound to it, and then we draw the array. And now we don't want to do 6, this is just I misclicked, but this should work fine. So that's how we're drawing our triangle. Now you'll notice if I go and change the color in our fragment shader, like if we take off the green in here, then we should get a red and blue purple color, I guess it would be. Yeah, a purplish color. So you can see how that works. So now I mentioned earlier we were going to look at element buffers. That's where we're going to do that now, which is going to be another step. So basically the idea is, if we go into Paint again, so imagine you have a square, right? In OpenGL, a square or a rectangle, a quad, is always comprised of 2 triangles, like this, or like this, or any other way a triangle could be made in there. So you have these. So technically you can have here. Let me get this. I need this bigger. So you can have, each triangle would normally be, why? Give me a big brush. All right. So each triangle has three vertices, right? Like this. So this one has 3 and this one has 3. Now, if we were to do it using the vertex array, we'd have to define these 3 vertices, and then we would have to define these 3 vertices in the array. And you'll notice that these 2 vertices on the corners that are shared between the 2 triangles. Now, in this case, an extra 2 vertices isn't going to be a big issue, but in large meshes, large models, you're going to have a lot of repeating data. And vertices, vertexes, as you can see, can actually have quite a bit of data inside. So eventually, if you go to animation and stuff, there's going to be other stuff in here. There's going to be like bone weights and bone indices, and there's going to be a whole bunch of data. And if you have a bunch of duplicate data, you're wasting a lot of memory on the GPU and possibly on the CPU. Now, the one caveat I'm going to mention now, and I'll mention it again later, just because it will come up, is I mentioned lighting again and the normals. So imagine you had a box here that goes off like this, right? And there would be here. Now, you would think that you could have one vertex that shares between this triangle, this triangle, this triangle, and the one on top, right? But since all of these have a normal that say which way is the outward facing, the normals, you're going to actually need to define this normal, this vertex 3 times, because otherwise you're going to have bad lighting, or it's going to be saying that this vertex is pointing left, but for this face we need the vertex pointing right, and for this one it's pointing up. So you just got to be aware that whenever you have a vertex that you have a vertex that could be shared geometrically, if they're shared between 2 faces that point in different directions, you either need to define the vertex twice to be able to do flat shading, or you can share the vertex, but you need to get you need to calculate the normal so that it's actually pointing somewhere down the middle, so that anyone using this vertex would get a smooth shading going around. And that's the difference between, if you go into Blender, the 3D modeling program, and you choose flat shading and smooth shading, I believe this is basically what they're doing. I don't know if they're changing how vertices are shared, but that they're changing the normals to be either facing the direction of that or interpolating between the faces like that. So it's just something to keep in mind. We'll visit it again in a future section when we get to lighting and we start doing that kind of stuff. But for now, just remember that we want to share vertices, and that's the point that we're getting at now. So let's make that box, right? We're gonna make this box. So let's start thinking about how this box would be made. So let's put an axis down the middle here, like this. Axis down the middle this way, and we'll assume the middle is 0, 0. So our vertices are going to be at, and we'll do one triangle at a time, minus 0.5, 0.5, and then minus 0.5. So let's go up here. Now I'm going to define these. It might not be exactly the same as what's on Learn OpenGL, but I'm showing you how you would calculate these. So we're going to do x values first, minus 0.5, 0.5, minus 0.5. So minus 0.5, 0.5 minus 0.5 for the first triangle. For the y value, you got, so we're looking at the y axis now, minus 0.5, minus 0.5, 0.5. So minus 0.5, minus 0.5, 0.5. So that's all good. Now, if we look at, if we run this now, you should see that the triangle we have now falls basically into that shape. See? All right. Now we're going to use vertex sharing. So I'll show you how you would need to define this again normally. But so if you want to do this again using what we have now, you would say minus, so we'll start with this top left corner. So x value is minus 0.5, 0.5, 0.5. So we'll actually take all of these, and this is going to look a little bit ugly for no. So it'll be minus 0.5, 0.5, 0.5, 0.5, 0.5, and it's 0.5 minus 0.5, 0.5. 0.5 minus 0.5 and 0.5. And if we do 6 now, instead of 3, we draw 6 triangles instead of 3 triangles, and we play this, you're going to see that we have a rectangle just as we had it defined here, right? Now, this is drawing 6 vertices, but at this point, we actually want to be making sure to be drawing it with indices. So ideally, we define the first 3. We just want to define this last vertex. So if we go here, the last vertex was this one here. So 0.5, 0.50, right? 0.5, 0.5. See, now we only have 4 vertices. Now, what we need is what's called an element. Now what we need is what's called an element buffer object, or EBO, or index buffer is what I usually call it, because I think it's in Vulkan and in DirectX they're usually called index buffers. OpenGL calls them element buffers. So in our application, we're going to make another GLUint. So these are handles. They're integer handles to a resource on the GPU. So element buffer object, EBO. Now we're going to use the element nomenclature because the rest of OpenGL uses the word element. So using it in your OpenGL program will make it so you can think about it easier. So now here where we generate our buffer, we want to generate one more buffer, GL gen buffers 1 and element array buffer object, right? All right, so then after our vertex array, we want to bind our buffer. Now instead of an array buffer, element is an element buffer, element array buffer, yeah. And then it's going to be our element object. And then we need to bind the buffer data like this, right? So it's going to be basically the same thing, but we need to define it. So the element arrays are only indices. So you can take a std vector, and I like using the uint32t type and indices or elements. Instead, I'm going to stick to the elements naming, so we'll say elements. All right, so now remember that we need to provide this data in counterclockwise drawing order. So remember, I give vertices 1, 2, 3, and then 1, 2, 3. So that's basically what you do in this vertex array. You say, okay, so we're going to draw everything one index at a time, and the order of the indices that we pass in, one element at a time, and the order of the elements that we pass in is going to be how it's drawn. So let's say we want our vertices here. I'm going to label them now just so you can follow along. So this is 1, 2, or actually here. So we define these as 0, 1, 2, and 3, like this. So that's the order of inside the array. 1, 2, 0, 1, 2, 3. And that's basically what we want to do. So the first triangle is 0, 1, 2. So we just put simply 0, 1, 2. And then the second one is 0, 2, 3. And then the next one, 0, 2, 3. And this could be the same. It could be 3, 0, 2, or 2, 3, 0, or 1, 2, 0 for the first one. It doesn't matter the order as long as they are in counterclockwise order, right? And with that done, we just do our GL buffer data. So GL buffer data, GL element array buffer. It's going to want a static cast again. Static cast, GL size, I pointer, vertices, indices, elements dot size times size of uint 32p. Why is this being, oh, I forgot a bracket here. And then this is going to be the data itself, so elements.data. And it's going to be the same thing as before, GL static draw. Like that. And that gives you your element buffer. It's complete, it's uploaded and everything. Now the only change we need to do down here is in our draw call. We can change this to GL draw elements, GL triangles. We have to tell it what kind of, so GL triangles, how many? 6, just like before. But there's a couple of other things. GL enum is it's what data type is the are the indices, because you can do regular ints, you can do unsigned ints, you can do floats, I think. So what kind are you using? We are using GL unsigned int. What can I do? 32? No. Unsigned int 8888, I think. This is 32. But I think GL unsigned int should work fine. And then the last element is what the starting. Yes, this is an offset into the buffer. So sometimes you'll have a really big index buffer to save space, and each object will represent a small portion of it. So let's say you want to draw, like you could start 12 elements into it and stuff like that. I'll put null pointer, even though. Either way, so that should give us the same thing. I didn't screw up. I screwed up. How did I screw up? Okay. 0, 2, 3. Oh, sorry. 0, 0, 1, 2, 0, 1, 2. So -5. -5, 5. Oh, I did this wrong. -5, 5. -5, 5. -5. Oh, I did it the other way here. So let's fix these. So this is -5, 5. So this is 1. So I had these in the wrong order for some reason. So I'm gonna fix these. -5, 5. -5, -5. 5, -5. And 5, 5. Okay, so I had those ones in the wrong order for some reason. I want it to match the picture. Yeah, so there we go. So I had the order wrong, but you get the idea. Now, the final thing we want to do is it's going to ask you, and this is not going to be very difficult because we've already done a lot of the setup, but the assignment 2 is expecting a triangle that looks colorful like this, right? So to do this, what you're going to need to do is you're going to want to be able to use these color values that we're passing in, right? So we're going to say that we want yeah, we'll figure it out in a second here. But let's just say that we want to pass in. We want, instead of it just being white, we want to be able to change it to red without it. And you know, one corner, let's just say, is going to be blue, and it's going to show. It's going to be green, and it's going to show kind of what we're getting at here. So this is going to be fairly simple. We've done most of the work. We just really need to change our shaders now to get this working. So for our shaders here,
what we want to do is we want to take this color and we want to give it to the fragment shader to use, and that's basically all we really want to do, right? So we want to define a color that's going to be output. So we'll say out vec4 vertex color. And this is literally just going to take the color that's brought in, so vertex color, and it's going to do the exact same thing that we're doing with the position, basically. Vec4 color, and then we're going to put a 1.0f at the end of it, like that. Now, we want to take this vertex color into our fragment shader, so we'll say in vec4 vertex color. Now this needs to be the same type and name as what you define up here. Now you do that, and then in our frag color, we'll just put vertex color. And now that should be all you need to take in the colors. And you see, we have it all red except for a green corner. Now you can kind of see that it's already, you might have expected it to be hard green and then hard red, but we get this nice gradient. So that's because anything that you any out variable from your vertex color that goes on forward gets interpolated between values from one vertex to the next. So when it goes from here, the fragment color is by pixel, right? So when it's getting a pixel over here, it's taking the green value that we have at this vertex and the red value at this vertex, and it's saying, okay, I'm halfway between them, so let's do an orangish color or whatever. And same thing in the middle here. If you're in the middle here, it's going to be taking like 30% of its color from here, 30% from here, and 30% from the other vertex, and it's going to blend them all together, and it's going to get a color, right? So with that being said, to get the rainbow colored thing that you look like here, we're going to make one blue, one green, one red, and then the fourth one, I don't know what we're going to do with it, but you can figure out what to do with that in your assignment. So one red, one blue, one green, and let's just say we're going to put one that's like, I don't know, half in between all of them. 0.5, 0.5. Now if we replace that, you'll see we now have our nice little rainbow color. The one that's halfway between is like halfway between muddy color here, but the one color down here is correct. So now if we take this and we only draw the one triangle, the first triangle, you're going to see that it looks a lot closer to the original screenshot that we were going for, with the colors kind of reversed, and since we made it into a square, it's not exactly the same, but you get the idea. All right, one last thing to finish off this lesson. We're going to abstract this out and make this reusable so that later on, when you start making more shapes, this is makes a lot more sense for you. So what do we want to do? Let's start with the interface. Let's just say we want to be able to just say mesh.draw. I think I think this is basically what we want to do, and all of this can be probably brought down, and probably as in it can be brought down if we keep these indices here. We want to say mesh triangle mesh is equal, or is equal, but I'm just going to do initialize. I'm just going to use the initializer, and we want to pass in the vertices and indices, and basically just have it do everything, or vertices and elements, and basically have it build it itself, right? So that's basically all we want to do, and this is extremely possible, and will make everything a lot easier. So what we're going to do is we're going to create a new class. I like using snake case, and this is going to be called mesh. It's going to be our mesh class. We're going to create it, and it's going to be capital M actually. We're going to make this pragma once. Now, I want to mention, because I had a night to think about it. Usually you have a separate include directory when you're making a library, and your things are going to be you're going to have a public interface and a private bunch of stuff, and usually the H files would live in the same source folder here. I don't like really big source folders that have a whole bunch of stuff in them, and like a bunch of .h's, a bunch of .cpp all in the same folder. We can break stuff up, but we're going to keep it like this for now. We'll reload to CMake project after you move your mesh.cpp into your source folder. All right. And oh wait, I should mesh.h like that. Okay. Class mesh. So, well, what did we say? We had a public, and it had a constructor that took a reference. And what we're actually going to do is we're going to say std vector vertex, and we're going to use a double ampersand here. This is for it's move semantics. For basically, we want to move the vertices from the application class into here and take ownership of them. So that's what this is doing. Vertices and std vector un32t indices. So we have a constructor, and we also want a draw command. Right. All right. So let's include some stuff. Pragma1, include vector, include types. All right. Good. All right. Now we can define these. So to create our mesh, we literally just take the basically take everything in here. Now the shader, we're going to hard code the shaders for now, because we're going to make those, we're going to abstract that out even more later as well. But realistically, all of your objects are probably going to use the same shader. So you can probably just take all of it like this and do this all the way down to delete shader like this. Boom. And then we put this all inside our constructor like this. Now you see we're missing a bunch of includes, so let's a bunch of stuff. So let's do that. So in our application, we have basically all of this stuff can go inside of our mesh as private variables. And you'll see we need our OpenGL header here. Probably just keep glad like that. Now what else do we need? Not much. Elements. So this will be, I call this indices again, elements. Like this. We need IO string. And I think that might be all of it. Yeah, all right, that's there. Now our draw command, and that again, it's gonna be fairly simple. We literally just take these three and put this inside our draw, like this. Now we've got an abstracted mesh class, a very basic one, and one that should not stay like this forever. Like these shaders should probably be more dynamic, being able to choose what shader you want to do, and stuff like that. You might want to cache your vertices and indices for whatever reason, but for now, this is more than good enough. So we want to bring in our mesh class here, but we'll actually do it in our application. So what we're going to do is we're going to say include mesh, mesh.h, and we're going to say mesh like this. And then inside our application.cpp, we're going to say our mesh is equal to this. requires one argument. What? Two are provided. Maybe I need to do this. Maybe it wants me to do this even. Because this is move semantics. What I was thinking was going to take ownership. But usually I'll very often I'll cache my vertices and indices. Actually, I will cache my vertices and indices, and you'll see why in a minute here. Because I just thought of a flaw. But anyways, we'll take mesh. We'll do here. Now we have it small draw. We want a big draw because it's public. So we'll go back here and we'll change this to capital draw. Capital draw. And that brings us to our flaw. So here we have a hard-coded 3, but what if the mesh is much bigger than just one triangle or 3 vertices? What we want to actually be doing is we want to be taking the number of elements here. So what you can do, you can either just cache the number of elements, or you can cache the entire thing. I will cache the number of elements right now because it's smaller. So we'll say uint 32t element count. And this will simply in our constructor here at the end, just because once we know that everything is good, we'll say element count equal elements dot size. And we will put element count. There we go. Now what is this doing? Whatever. So now if we hit play on this, it should still work exactly the way it did, but it doesn't. No appropriate default constructor. Oh, it wants a default constructor. Okay, well we'll give it a default constructor that does nothing. Give it a default constructor. Now when we play it, it builds and it draws our triangle. Now, the reason we do this now is, let's say we want, just an example, we want to add, let's say let's take this, we'll move it down. Say we want to add a hat to it, right? So we want to add another vertex up here. That will give us a nice hat, right? We want to do one of these. So our fifth vertex would be 0.51, right? It would be 0 and then 1. So in our vertex, in our application here, we will take this, we'll create one more here. It'd be 0 and 1. And now our third triangle is going to be 0, 3, 4. 0, 3, 4, like this. Now that should have given my thing a nice little hat. And it gave it a hat, right? Now let's say we want multiple meshes, right? So instead of doing this like this, we want multiple meshes. So what we can do is we can, in our application, we can keep a vector of meshes, vector mesh. We'll say meshes, and we can actually get rid of this one. And that means we can get rid of our default constructor that I didn't want anyway, because it makes no sense to have a mesh without anything in it. And now we got some red, that's fine. What we'll say is meshes dot in place back. And we will take these arguments out and put them in here. So that creates the first mesh. Okay, so we've got our house with a hat as the first mesh. Now let's say we want to put a little triangle like here. Let's say we want to put a triangle like right here, right in the middle. So that it'll assume that we're doing 0.25 now as the middle point. So we want it like right in the middle of all of this. So it'll be we need new vertices and indices, but we can say just at this point say vertices dot clear. Elements dot clear, and actually we're just going to do this again. So we're going to say vertices 2. We can actually just do this. Vertices equal elements equal this. So we're not going to redefine it. We're not going to make a second one. We're just going to recreate. So where do we want it? Minus 0.25. So we're only going to have 3. Minus 0.25, 0.25, 0. So minus 0.25, 0.25, 0. And then minus 0.25 on the y, minus 0.25, and then 0.25. Minus 0.25, minus 0.25, 0.25. And we said we wanted to make it a red triangle, right? So let's make it red. And now all we need to do is do meshes dot in place back, vertices, elements, boom. And again, you want to be able to just move these over. There. So that we're using move semantics specifically because I'm assuming that at some point we're going to be caching these vertices and indices, but we don't want to cache them. But you can just make these cost references and you wouldn't have to move them all the time. Now inside of mesh.draw, what we would actually do is we would iterate over all of our meshes in the array or in the vector, and we would say mesh.draw. And now we should have exactly what we were expecting. Something weird. I don't know why there's black there. That is a little bit odd. Oh, so you can see here my element array was too big, so it was trying to draw data that wasn't there. It was going into garbage data and drawing garbage data, and it's still blending a weird color over here. 012. Oh, that's why I saw it. There is an extra 1 there. There we go. Now it should be pure red, which is what we wanted. Pure red. There we go. And that's exactly what we had inside here. So you can see this is going to be the end of our journey into week 2. I understand that this was probably a very long lecture. I talked on for several hours, but this sets you up for success moving forward, being able to do everything that they ask you to do. Now, the exact requirements of assignment 2 I'm not going to get into because I'm taking this class as well and I might not get good grades. I don't want to give you bad advice, but using OpenGL, I'm confident that what I'm showing you here is a solid way of doing it. Not the best way of doing it, but a very solid way of doing it. Okay, so that was our foray into shaders and buffers and element and vertex arrays and some of the more heavier content that's going to take longer to explain. This week is probably one of the bigger ones. So next week I'm going to show you how to build a 3D object, not a pyramid, because if I showed you a pyramid I would just be giving you the solution to your assignment, to one of the assignments, but we're going to make a cube probably. I showed you how you would go about thinking about a cube in this mess of a drawing here, but we'll make a cube. I'll show you how you would think about a cube and how you would put all that together. We're also going to look at the view matrix and the projection matrix so that you can get depth in your scene and so that you can have a camera to place somewhere in your scene. It might not be fully interactable, but you do need to be able to, it looks like the milestone will expect you to be able to at least have a camera pointed somewhere so you can point it at an object that you are supposed to create. It's not that much. It's actually very little code on top of what we've already done. Everything that you need to do these assignments is really here except for the camera stuff. So we're probably going to start off with, there's going to be a small video on how do you create a 3D object. We might do a cube. I might show you how to adapt SNHU code to create a sphere and stuff like that, because that's can be tricky. But then I'll show you the camera stuff as well, where we're just going to take a camera, we're going to place it like, let's say 5 units back and a couple of units up, and we're going to say to point at the root of the scene, which is at 0, 0, 0 of the scene. That way you can point your camera there and you can place all your objects relative to that 0 point, and it'll be a little bit easier to work with. And there's going to be stuff like transforms, so our meshes will have a transformation on them, so you'll be able to, they should be able to move in space. That will be, we'll be expanding our mesh class for that, and all that. So anyways, hope you enjoyed week 2. Sorry for this very long info dump, but doing it right once now in 2 hours will save you a lot of hours in the future. And you can ask a bunch of people, anyone who's taken this course before, this should help you. Yeah, so see you next week.